Okay, in this video we're going to talk a little bit about network address translation. Now, to lead into NAT, we need to speak a minute about IP version 4, the Internet Protocol version 4. IP version 4 uses 32-bit addresses. So anytime you see something like 123.45.6.7, each of these four numbers is one 8-bit number, so it can vary between 0 and 255 with some exceptions for things that aren't allowed. So 4 octets of 8 bits each equals 32 bits total. Now, with 32 bits, this gives you 2 to the 32 total addresses. Spell, the sum total of which is approximately 4 billion. Which sounds like a lot until you realize that there are already 5 billion people on the planet, or more. Actually, are we up to 6 now? So we have less than one IP address per person on the planet. Now, think about how many devices you own that each have an IP address, and you're probably talking 3 to 4, maybe some of us, if we're ambitious, have 10. We don't have enough IP addresses to go around, at least not IP version 4. We are eventually going to address this by going to the Internet Protocol version 6, which has 128-bit addresses. But that's still a bit in the future. And so right now we're stuck with IP version 4 as our primary Internet protocol. So what this leads into is we have to come up with some way to reuse addresses. And NAT is one of the procedures that is used to do that. Now, I'm sure all of you, or most of you at least, have a little network at home. You have a broadband router. It's just connected to your cable modem probably, or maybe DSL, which is connected to the larger internet. Behind this router, you probably have 3 or 4 computers, maybe a PC and a laptop, maybe a smartphone. Talks on the wireless. Maybe you've got a Nintendo Wii talking on the wireless. If you get down into the configuration details of these things, you'll notice most of them have an address that looks something like 192.168.1.say 100. The last 2 octets will change, but in almost every case they're going to be 192.168. dot something, and usually it's .1 dot something else. Addresses with this prefix are what we call the private address space. One of the features of the private address space is that it is not globally routable. What this means is that a router, which has a gateway built in, if you recall, a gateway connects two networks. Let's say we'll do this. So here we have 2 networks. Each one with a gateway. If this is a private IP space, You cannot send messages from this network to a machine in this network. It won't happen. The routers are programmed not to forward those packets. Machines within a network can send to each other, but they can't send outside the network, or nor can they receive from outside the network. So what this boils down to is you can have many networks on the internet that have machines with a private IP address, but those machines cannot talk to each other. Within their own little local networks, they can talk, but they can't communicate with other networks out there. The upside of this is that we can reuse certain IP addresses. The downside is machines that have those private addresses cannot talk to each other. NAT is a bit of a hack on the system that lets us do just that. So let's do 2 routers. Actually, we'll just do 1 router to make the example a little easier. I'm going to move some things around. Router is connected to the internet, and somewhere out there is the machine we're going to. So we're going from point A to point B. This router actually has 2 network cards. And we'll say one of them has a globally routable internet address. And we'll say for B it's got that, which is also a globally routable internet address. And behind this router, we have a private network in the 192 range. So we have machines that look like that. Now, as I mentioned before, B, which has a globally routable address, cannot talk to A, which has a private address, and vice versa. Even though there is a path from one to another, they cannot talk simply because those addresses are not allowed to speak. What can happen, though, the router is part of this private network. So it's going to have a 192 address. It's the .3 as well. So it can speak to A, and A can speak to it, but A cannot get outside the router. So what we're going to do is we're going to apply network address translation at the router. And the easiest way to do this is to set up a grid of source and destination IPs. For each step of a packet's path through the network. And let me annotate my diagram just a little bit more. So we're going to look at 4 legs of a journey. And this is a journey where A makes a request of B and B sends a response. So the first leg is here. A sends its packet to the router. The second leg is sending the packet from the router to B. Third leg is from B back to the router, and the fourth leg is from the router back to A. Now, at each step, I'm going to illustrate the source and destination IP addresses for that packet. Now, do them in blue just to make them stand out a little bit more. All right, so at step 1, we're sending a packet from A to the router. Now, the kicker here is that A thinks it is sending to B. So in other words, the destination is B's IP address. And the source is A's IP address, 192.168.1.1. It's okay to do it like this because our destination is not a private IP address. So A sends the packet through the network via the router because the path it takes goes through the router. Now the router sees this packet going through, sees that it comes from an IP address on the inside of the private network and says, aha, I'm going to make it look like that packet came from me. And so it rewrites the source to be its globally routable IP address. And it's going to remember that that packet originally came from A. We won't go into the detail of how it does that. The destination remains the same because it's still going to B. So that's what happens along the path from the router through the internet to B. Okay? Now, B is going to make a response on leg 3 of the journey here. For its response, it's simply going to swap the destination and source packets. So it's going to set itself as the source. And it's going to set the router's IP as the destination. And the reason it sets the router as the destination is because it thinks the packet actually came from the router. So that packet goes back from B to the router. And now the router must rewrite the destination IP address to be its real destination, which is A. Source remains the same. And that, in a nutshell, is network address translation. From the standpoint of B, the entire transaction was with the router, which, since it has an IP address, is just another machine on the internet as far as B is concerned. However, the real communication was taking place with A, which is a private address hidden behind the router. From the internet standpoint, A, C, the other machines behind the router, X, Y, and so forth, don't exist. There is only the router, the machine that's providing network address translation. But it hides all these other machines that are on its network and allows them to communicate, albeit in a somewhat more limited fashion, with the rest of the internet. Your broadband router at home performs this kind of network address translation. If you go into the settings of your router, you'll notice that there's a place where you can see its globally available IP address. This is an IP address that is assigned to you by your ISP, and all traffic that you send out to the internet and that you receive from the internet, the rest of the world thinks it's communicating with your router. It doesn't actually see your PC or your Wii or your smartphone or your laptop, anything that you have behind connected to the internet via the router. All it sees is the router, and it's because of network address translation. So, all right, well, that was a quick intro to NAT. Again, if you have questions, please let me know, and I will do my best to help you out. All right.